Good morning, dear students. My name is Ferhan Mazher, and today is 11th of March 2022. Right now, I am with the 11th Cambridge class, and the subject we are studying is Physics 5054. Today, we have set our hearts to solve a theory paper. We have selected October-November 2016 2-2 paper. This paper 2 belongs from the zone 2, or you can say the variant 2. The paper consists of two sections, section A and section B. The section A of this paper we have already solved in a video, and that video has been uploaded. Today, this is the second session on this paper, and today we are going to solve the section B of this paper in this video. And this section B consists of three questions, and we will solve all of them. So let's start today's paper. Okay, so the first question coming up on your screen. A spring is taken from a drawer in a physics laboratory. Figure 8.1 is the extension load graph for the spring. So here we have figure 8.1. On the y-axis, we have the extension in centimeter, and on the x-axis, we have load in newtons. So he says, using the figure 8.1, determine the load on the spring when its extension is 4.9 centimeter, 4.9 centimeters. So here you can see this is 4, this is 6. So with the 5 small squares, they have represented 2. So divide the 2 with the 5, so you get 0.4. So each small square on the y-axis represents 0.4. Because I want to know 4.9, so 4.9 will be approximately after 4, 2 small squares, a little bit above the 2 small squares after 4. From there, I will go to the graph, extension load graph, and when it will intersect the extension load graph, I will check what's the value of the x. So let me show you. So we are going to the question number 8. So here we go. So here 4.9, from here I will go to the graph and I will check what's the value here. This value here is 0.85. Okay, so it's approximately 0.85, 0.86, 0.85 Newton. So this is how you use that figure to find out the load when the extension is 4.9 centimeter. Hopefully you understand. Okay, then he says the point x on the figure 8.1 is the limit of proportionality for the spring. On the figure 8.1, sketch a line to show how the extension load graph might continue after x. Because here, this is the limit of proportionality. So up till this point, the extension load graph will be a straight line, its gradient will be constant. But when you have crossed the limit of proportionality, this graph will be no more a straight line, it will bend upward, showing that the extension and the load, they are no more directly proportional to each other. So let me show you. So here you can see I have shown after the x point, which is the limit of proportionality, the graph will be no more a straight line, its gradient will be no more constant, the graph will become a curve and it will bend upward. Okay, so here we go. Then he says, that was the B. Now question number 6, B part. He says that a rectangular plastic block is suspended from the lower end of the spring. Figure 8.2 shows that the bottom 3.5 centimeter of the plastic block is in the water in a beaker. So here you have a support, here that you have a spring, a plastic block is hanging with the spring, and some of the block is immersed in this water, which is in a beaker. The depth of the block which is inside the water is 3.5 centimeter. The question is the density of the water is 1000 kg per meter cube, and the gravitational field strength G is 10 newtons per kg. The base of the plastic block is a square with the sides of 4 centimeter. Calculate the pressure due to the water at a depth of 3.5 centimeter below the surface of the water. Okay, so the formula is very simple. If you want to find out the pressure due to the water or the pressure of the liquid, the pressure is equal to rho GH. So rho means the density and G and H. So rho is 1000 and the G value is 10. And the height, the depth of the water, we will convert this into meters. 3.5 centimeter, you divide it with 100, it will be converted into meters. So you will have 1000 multiplied 10 multiplied 3.5 divided by 100, and that will give you 350 Pascal. Okay, so then he says, calculate the upward force on the base of the block due to the pressure of the water. Now we know the pressure of the water, and we also know the area of the bottom of the block. So I can find out the force exerted in the upward direction due to the pressure of the water. The force is equal to pressure multiply area. So let me show you. Okay. So the force is equals to pressure multiply area. The pressure is 350 Pascal. The area is a shape of a square. Each side is, 4 centimeter. So I will convert the area will be length into length, and that will be 4 divided by 100 multiply 4 divided by 100. Why dividing with 100? Because we want to convert the centimeters into meters. So the area will be meters square. So in your calculator, you will write 350 multiply 4 divided 100 multiply 4 divided 100 equals to, so the force will be 0.56 Newton. Okay, so then he says in the figure 8.2, the extension of the spring is 4.9 centimeter. Using the answer from the figure A first and the answer from the B second, determine the weight of the block. The weight of the block is the extension produced is 4.9 centimeter. We know that from here, the extension produces 4.9 centimeter. So the weight will be the upward force plus the force which is needed to produce the extension of the 4.9 centimeter. This is a very conceptual thing which I'm just saying, that the weight will be equals to the force which produced that extension, and and it will be so the weight is a very conceptual thing, the weight which is downward, and the upward force is the force due to the pressure, and the weight should be equals to the force which is producing the extension, and the upward force. The upward force is 0.56, and the force which produced the extension, that is 0.85 Newton. So you add them, that will be equals to the weight. Okay. So 1.46, 1.41 Newton. So which will be 1.4 Newton. It's a very, very conceptual thing. Okay. So let's move to the next part. He says in the equipment shown in the figure 8.2, the pressure of the atmosphere is transmitted through the water. The total pressure in the water at a depth of 3.5 centimeters is larger than the pressure due to the water alone. Explain why in this experiment atmospheric pressure does not affect the position of the plastic block in the water. Because you see, when you put a plastic block in the water, The top surface of the plastic block is subject to the atmospheric pressure, and there the force due to that atmospheric pressure will be in the downward direction. And the portion, the bottom of the plastic block is in the water, and on the water, the atmospheric pressure is also acting. So that pressure combined with the water pressure causes an upward force at the bottom of the at the bottom of the, you can say, block. So on the top of the block, the atmospheric pressure is producing a force in the downward direction, and at the bottom of the block, the atmospheric pressure is producing a force in the upward direction. So both these forces on the top and on at the bottom, due to the atmospheric pressure, is cancelled with each other. That's why the effect of the atmospheric pressure does not affect the position of the plastic block in the water. Hopefully you understand. Let me show you the my written answer. And here we go. So the atmospheric pressure causes force on top of block in downward direction. Same amount of force acts on the bottom of the block in upward direction due to the atmospheric pressure. So its effect is cancelled. The effect of the atmosphere is cancelled. Hopefully, you understand these answers. And let's move to the next part. He says a force is a vector quantity. Force is a vector quantity and pressure is a scalar quantity. State how a vector quantity differs from a scalar quantity. The vector quantity has magnitude and direction both, whereas the scalar quantity only has the magnitude, it does not have direction. So that's the difference between a vector quantity and a, you can say, scalar quantity. So how you will write this: vector quantity has direction as well as magnitude, whereas scalars have only magnitude. So that was question number 8C, second part. Okay, so let's move to the next part. He says it's a 3 marks question. The beaker in the figure 8.2 is gradually moved upward so that more of the plastic block is in the water. Explain what happens to the forces that acts on the block. You see, if you will move this, let me show you from the figure. If you will move this beaker little upward, what will happen? More of this plastic block will be submerged, and due to this, the force acting in upward direction due to the pressure of the water, that will increase. The force exerted by the spring, that will decrease. The weight of the block will remain constant. So these are the three forces which are acting. So this is what will happen with these forces. So let me show you my written answer about these forces. Okay, the force due to the water on the block increases, force due to spring decreases, weight of the block remains constant. So let me show you the marking scheme. So I think we are done with the question number 8, and let's have a look at the marking scheme first of all. So our answers from 0.83 to 0.86, our answer is right. Line curved upward, that is also right. 350 Pascal, that's right. The force will be 0.56 Newton, that's right. 1.4 Newton, that is also our answer is right. The C first part, atmospheric pressure exerts a downward force on the top of the block, cancels out the extra upward force pressure. So second part, vector has a direction in addition to the magnitude. And the D part, any three lines from force due to the water increase and force due to spring decrease, increased pressure at the base, and they add to give a constant value, weight of block or the total force constant. So our answers are right. So that was the marking scheme. Let me reduce the size so you can see the whole of the marking scheme for the question number 8 in a single glance. So you can pause the video and take your time and read this marking scheme carefully. Try to compare my answers, your answer, your teacher's answers with the standard, marking scheme. So that was question number 8. We are done with this. Okay, so let's move to the next question. He says, let me reduce size. He says, a vertical solenoid, a long coil with an iron core is held in a wooden clamp above a laboratory bench. When solenoid is connected in series with the battery, a switch as an ammeter and a variable resistor, there is a voltmeter in parallel with the solenoid. So figure 9.1 represents this apparatus, and you can see this diagram here. I hope you can see very clearly. So here we have the switch, ammeter, voltmeter. This is the solenoid. This is the variable resistor connected. Here we have the battery. He says a student closes the switch S and a current in the circuit produces a reading on the ammeter. State what is meant by the current. The current is basically the charge, the flow of the charge is known as the current. So let me show you. I have written this answer also. So the flow of charges is called current. The flow of charges is called current. Okay, so the next part is he says the battery consists of five 1.5 volt cells in series. The reading on the ammeter is 4 ampere. State the size of the electromotive force of the battery because you have five cells and each cell is 1.5 volt and they are connected in series with each other. So the total EMF of the battery will be 1.5 multiplied 5, and that will give you the total EMF of the battery. Okay, so here we go. So 5 into 1.5, that will be 7.5 volt. Okay, so let's move to the next part. He says, calculate the total resistance of the series circuit. Because we know the current coming out of the battery, that is 4 ampere. We know the total EMF of the battery, that is 7.5 volt. I can calculate how much is the resistance of this circuit because the EMF is equals to, the EMF is equals to uh, IR, the current coming from the battery multiply the resistance of the whole circuit. So the resistance of the whole circuit will be EMF divided by the current coming from the battery. So we can calculate easily the resistance of the whole circuit. I is equals to EMF divided by the total resistance. So you will have the current coming from the battery is 4 ampere. The EMF is 7.5 volt. The total resistance is the question. So R will be equals to 7.5 divided by 4, and that will be 1.875 ohms. So it's when you round it off to two significant figures, it will be 1.9 ohm. So the total resistance of the circuit will be 1.9 ohm. Okay, so then the question is the reading on the voltmeter is 6.5 volt. Calculate the power dissipated in the solenoid. I know the current flowing through the solenoid, and I know the voltage drop on the solenoid. So the power dissipated at the solenoid we can calculate easily. The power is P is equals to IV. The P is equals to IV, and we can easily calculate P is equals to IV. The I is 4 ampere and the voltage is 6.5 volt, and so 26, so 26 watts. So the power dissipated will be 26 watt. Okay, so the next question they are asking is the solenoid is made of copper, and the student notices that as time passes, the solenoid becomes extremely warm. State and explain the effect of this temperature increase on the ammeter reading. You see, as the temperature will rise, the resistance of the copper will increase. So that solenoid will increase. So what will happen? The resistance of the whole circuit will increase. Due to this, the current coming from the battery will reduce and the reading on the ammeter will decrease. So that's the fourth part. Okay, so here we go. Question number 9b, fourth part. As the temperature increases, the resistance of the solenoid increases. So the current of the current from battery decreases. Reading on the ammeter will decrease. So that's the question number 9b, and its fourth part. Okay, so we have the next question. Question number 9 is C. First part, he says the current in the solenoid magnetizes the iron core so that the lower end of the core is the north pole. On the figure 9.1, draw the pattern and indicate the direction of the magnetic field in the region surrounded by the iron core. So, if the north of that electromagnet will be at the bottom, so from here, the magnetic lines will come out and they will go to the top of the solenoid where the pole will be south. So from here, the magnetic lines will come out and here the magnetic lines will go in. So this is the pattern which will be formed around that iron core. This is an electromagnet, and this is how you represent its magnetic field lines. Hopefully you understand. It was a 3-mark question. The student holds an iron cylinder against the bottom surface of the iron core in the solenoid. When he releases the iron cylinder, it stays in contact with the iron core. Explain why the iron cylinder does not fall. You see, if you take an iron cylinder and place it here, if you place an iron cylinder and place it here, so when you will close the switch, this will become electromagnet. Due to magnetic induction, what will happen, that iron piece of iron will also magnetize. So if this pole is north, the top surface on the top side of that cylinder will become south, and the bottom will become a north. So there will be the like poles attract each other. So what will happen, the north of this electromagnet and the south on the top of that iron cylinder, they will attract each other, and obviously they will become in contact with each other. So this is the question they are asking. Okay, so let me show you my answer. So due to the magnetic induction, top end of the iron cylinder becomes south pole and the bottom end of the cylinder becomes north. North of the solenoid and the south of the iron cylinder attract each other, and that will be quite a strong attraction. And because the unlike poles attract each other. Okay, so the next question is, the switch S is opened, state and explain whether the iron cylinder remains in contact with the iron core. You see, when you will open the cylinder, open the switch, sorry, that iron core will be no more electromagnet. When it will be no more electromagnet, the iron cylinder, it will also lose its magnetism. It cannot retain its magnetism, so it will also lose its north pole, south pole, and obviously when it will be no more a magnet, so it will be no more attracted to the iron core, so it will fall. So let me show you my written answers. So the iron will lose its magnetism, so the iron will fall down. So this is the answer which we have written. So okay, so we are done with the question number 9. So let's have a look at the question number 9 marking scheme is showing up on your screen. He says the rate of flow of charge or charge flowing per unit time, 1.7.5 volt and 1.9 ohm and 26 watt, and resistance increases, reading of the ammeter decreases. C part, at least 2 lines left and 2 lines on right of the core. Correct shape by I, good shape by I, and into poles and no straight section, and at least 1 line on each side, at least one arrow north to south, primarily upwards, and none should be the wrong. None should be wrong. Cylinder is magnetized by induction. Top of the cylinder is a south pole, unlike poles attract or south pole attracts north pole. And the second portion, it does not remain in contact, and the iron is temporary soft magnetic material. Iron is a soft magnetic material. So when the iron core is no more a magnet, so the iron cylinder will lose its magnetism immediately. So, and that's why it will fall down. The material core and cylinder loses magnetism. So that is, my dear students, the answers from in the marking scheme for the question number 9. So let me show you again. So this is question number 9. Its marking scheme is showing up on your screen. So you can pause the video and you can take your time and read this marking scheme carefully. We are moving to the next question. A laser produces a beam of red light. The red light from the laser has a frequency of 4.3x per 14 hertz. State the speed of the light in the air. This is a fact, and you have to kind of remember this. The speed of the light in the air is 3 × 8 meter per second. You are supposed to remember this number. So we have 3 × 8 meter per second. Okay, so let's move to the next part. He says, calculate the wavelength of this red light in the air. We know the frequency of this red light, and we know the speed of the red light. So we can easily find out the wavelength. You remember the formula is V equals to F lambda. V equals to F lambda. So if you want to find out the lambda will be V divided by F, and the frequency is given here, and we also know, so very easily I can find out the lambda. So here we go. So V is equals to F lambda. So lambda will be equals to V divided by F. So it will be 3x per 8 divided 4.3 x per 14. So that will be 0.697 x per minus 6. So it will be 6.97 x per minus 7 meter. So it will be approximately 7 x per minus 7 meter. So that will be the wavelength. Okay, so the next question is, he said, red light from the laser strikes on one side of a glass prism at an angle of incidence I. The light refracts towards the normal as it enters the prism. On the figure 10.1 figure 10.1 shows the prism, the light and a screen. So what is the question? He says, state what happens to the light of the speed of the light as it enters the glass. So speed of the light when the light from air will enter into the glass, the light will enter from a rare medium into a dense medium. So the speed of the light will decrease. So it's a simple question. State what happens to the speed of the light. So let me show you my answer. So the speed of the light decreases. So here we go. So the next question coming up on your screen is, he says, the refractive index of the glass is 1.5. The angle of refraction in the glass where the light enters the prism is 30 degree. Calculate the angle of incidence. So this is the angle of refraction. The angle of incidence is question. So we know that the n, the refractive index, is equals to sine I divided by the sine r. So very easily by using this relationship, n equals to sine I divided by sine r, we can calculate the refractive index. So n is equal to sine I by sine r. So n value is 1.5 and the sine r, that's sine 30. So it will come to the left side. So it will multiply with the value of the n. So you will have 1.5 multiply sine 30 equals to sine I. So the I, so when you multiply 1.5 with the sine 30, it gives you 0.75. So when you make I the angle of incidence alone, the sign will go on the other side, it will inverse. So you will have angle of incidence is equal to sine inverse of 0.75, and the angle of incidence will be 49 degree. So the angle of incidence will be 49 degree. Then he says, then the light then passes back into the air and strikes the front of the white screen as shown in the figure 10.1. Calculate theta, the angle between the ray in air and the side of the prism. So we have to find out this angle. Okay. So theta will be 90 minus 49, and that will be, so we will apply the formula for the refractive index on that side where the light is coming out of the prism. At that, the angle of incidence in the dense medium is of 30 degree. We don't know what is the angle of refraction in the air. You know, the formula for the refractive index will be sine r divided by sine I. A special thing about the refractive index formula is that in the numerator we always put that angle, whether it is angle of incidence or angle of refraction, which is in the rear medium. So when the light came out of the prism, the angle of refraction is in the rear medium. So that's why n is equals to sine r by sine I. So we want to find out what is the angle of refraction. So 1.5 into equals to sine r divided by sine 30. So sine r will be 1.5 multiplied sine 30, and R will be 48.59, which is approximately 49 degree. So because we want to find out that theta, so I can show you, and theta will be 90 minus 49, and that will be 41 degree. Hopefully you understand this calculation, and let me show you and try to, I will explain to you. You see, first of all, I calculated what is this angle of refraction here. So once I know the angle of refraction, so this full angle is 90. So from the 90, I subtracted the angle of refraction. So I got this angle theta. So that was the third part. He says the laser in the B is replaced with the filament lamp and a slit as shown in the figure 10.2. A ray of light now strikes the prism. So a ray of white light. So you know white light consists of 7 colors. On the figure 10.2, draw what happens to the light as it passes through the prism and strikes the screen. So let me show you. It's a 2-mark question. So the light will split into its 7 colors. So this is what will happen. The white light will enter. When it enters into the prism, the white light will disperse, and the spectrum will be formed on the screen. Hopefully you understand. Okay, so now we are moving to the next part. Okay, so describe what is seen on the screen. Okay, so 2-mark question. Describe what is seen. A spectrum is seen on the screen, and you remember the code word Roy G. Biv, red, red, orange, yellow, green, blue, indigo, violet. So band of colors will be seen. Order of the colors will be red, orange from top to bottom. It will be like red, orange, yellow, green, blue, indigo, and violet. He says, in addition to visible light, the filament lamp also emits some of the infrared radiation. This infrared radiation is able to pass through the glass on the screen in the figure 10.2, mark an X to indicate the place where the infrared radiation strikes the screen. Infrared radiation has longer wavelength as compared to the visible light, and its frequency is less than the red color, so it will be here. So here above the red color, you will have the infrared. So hopefully you understand. So he says, infrared radiation is often detected by using a sensitive thermometer with a bulb that has been painted black. Explain why the blackened bulb makes the thermometer a good detector of the infrared radiation. You see, the bulb in which we have the mercury, that is painted black because the black is a very good absorber of the infrared radiation. So it absorbs infrared radiation quickly, faster. That's why we use it the black color on the bulb of the mercury. Black color is a very good absorber of the infrared, so that's why we used it. Okay, the next thing is explain the role played by infrared radiation in the intruder alarms. You see the intruder alarms, we have a very sensitive receiver of a detector of the infrared radiation. So if any intruder will come in a room where you have set the intruder alarm, so everybody, for example, a human body, it emits infrared radiation. So if a human will come in that room where you have set the alarm, from the human body, the infrared radiation is coming out. So the detector will detect then an increase in the infrared radiation, and it will start the alarm. So let me show you my written answer, and let's see. Human body emits infrared. Detectors detect change in infrared. So the intruder alarm starts the alarm. So that's it. So let's have a look at the marking scheme. So question number 10. So you have this is the speed, and that's the wavelength. We have, I think, let me check the answer. Yeah, that was our answer. Our answer was right. So here you have the degrees 49, 41, dispersion at both the surfaces, and refraction in correct direction, violet, blue, and light below the red below. Spectrum or band, continuous colors, and red, orange, yellow, green, blue, indigo, violet. X marked above the red. It is black surfaces, a good absorber of the IR and intruder alarm. Intruder human being emits infrared. Intruder worms or IR detected. So this is it. And my dear students, today we have done in this session October, November 2016 to 2 paper. And in this video, we have done the section B of this paper. The section A of this paper we have already done in a video, and that has been uploaded in the YouTube, and you can find it above this video in the playlist. So I have tried my best to explain you all the concepts involved in this paper. I hope that this video will be helpful to you in preparing your Cambridge exams. If you find this video interesting and useful to you, do share the link of this video onto your Facebook accounts and onto your Instagram accounts and onto your Twitter accounts, because that will help me promote my channel. So, my dear students, thank you very much. Have a good day and God bless you all.